In this DeBacco University video, I'm going to attempt to explain the quantum mechanical model of the atom, which is our more modern idea and concepts, which does bring in a lot of complexity, but hopefully I can kind of break it down so you can develop an understanding of this model. All right, with any development of any theory, you have to look at the context for which the theory was developed in. And this quantum mechanical model was developed primarily in the 1920s and emerged during the revolutionary period as scientists sought to explain the atomic behavior beyond the limitations of classical models. The Bohr's model, again, it was introduced, those orbitals, those kind of electrons traveling in that planetary model, but this did fail to kind of explain all of the details there, but was a good initial continuation step. Rutherford, Thomson, Chadwick, Millikan, all those established the nucleus. They discovered the electron. They started to describe some of the properties, but now we're getting into kind of the real details of the actual atom. So the electron comparison here, we're looking at, instead of electrons orbiting like planets, like I said in the Niels Bohr model, the quantum mechanical model, thanks to Schrödinger, describes electrons as exhibiting in what we call orbitals. So they're existing this kind of orbital space where there's a high probability of essentially finding them. So you went from this planetary kind of ringed model to more of an electron cloud, if you will, looking at the increasing density where you're more likely to find an electron. So looking at this, how does it relate to the Schrödinger equation? Well, the quantum mechanical model does rely on the Schrödinger equation for the calculations of those electron wave functions, but it also incorporates the Heisenberg uncertainty principle, Born's interpretation, known as the Born rule, and the Pauli exclusion principle. So we're looking at the position and momentum cannot be precisely known simultaneously, leading to the probabilistic orbitals, those denser clouds. The square of the function gives the probability of finding that electron, so the Born rule kind of ties into that. And then the Pauli exclusion principle says that no two electrons can have the same set of quantum numbers, explaining electron configurations, which will be described in another video. Now the quantum numbers here, we're looking at these kind of multiple numbers here and what they've kind of oriented, kind of equate to. So quantum numbers are electrons in an atom are characterized by 4 quantum numbers that define their energy, position, as well as their behavior. So if we look at the principle, kind of got a visual representation here, a little description here. So the principal quantum number, represented by n, indicates the energy level or the shell. Higher n means higher energy levels. So here we're saying energy level 1, which is quantum number 1, 2, and 3 in this simplified atom. The Esmil quantum number, represented by the letter L, defines the shape of the orbitals. So we get into S, P, D, and F shape. When we talk about the periodic table, we'll show you kind of where those are located. And this range is essentially from 0 to n-1 when we're looking at defining that. And that's going to again be the shape of the orbital. And then the magnetic quantum number, M subscript L here, specifies the orientation of the orbital. Is it basically a positive orientation or a negative orientation? And then the last one, the spin quantum number, M lowercase subscript s, as the name describes, it describes the electron's intrinsic spin. So basically a positive or negative spin, we could see here. So when we put all these together, this is how we're developing that more complex and more hopefully realistic vision of how the atom looks with those electrons. So key features of this quantum model are the wave-particle duality. Electrons exhibit both particle-like and also wave-like properties, which is part which makes them so complex. We like to think of them as orbiting in those fixed paths like the Bohr model, but electrons really describe more accurately in a wave function, which represents the probability of finding them in a particular space. Those orbitals I described are where the electrons reside, which is this 3-dimensional region now around the nucleus where electrons are most likely to be found, and this is defined by the Schrödinger equation. So unlike orbitals that describe probability distributions, not defined circular paths. So those orbitals I've been talking about, the shapes, again, just to look at the comparison of them, we'll dive into more detail going forward. The equation's solution also explains the complex shapes of orbitals, whether they're spherical, they could be dumbbell shaped, they could have more of a clover leaf, they could have these different geometries, which in part influence their chemical bonding as well as their molecular geometry. Now the basics of the Schrödinger equation, the model is based on the Schrödinger wave equation, which is mathematically describes the wave functions of electrons. The square of the wave function gives the probability of the density of finding those electrons in a specific region. Essentially, it's kinetic energy plus the total potential energy is equaling the total energy, I should say. So kinetic plus potential is equaling the total energy. We won't dive into too much of the detail here. We're looking more just that kind of overview and what it's basically showing us. So the Heisenberg uncertainty principle, this is the concept that it's impossible to know both the exact position and momentum of an electron simultaneously, which leads to the probabilistic nature of electrons located in those orbitals. And that's why I see sometimes denser and less dense areas indicating the denser areas higher probability, less dense, less probability. And this is all evident when we zoom out that electron cloud. It's our visual, if you will, of the probability of where you're likely to find a nucleus. Again, with those denser regions indicating a higher probability. Now, how does this relate to the atomic theory just overall? Well, in comparison to Dalton, Thomson, Rutherford, Chadwick, and Millikan and Bohr, we have this kind of building on all of those. So this is our final kind of model here, looking at tying all those previous concepts in. Dalton's indivisible atoms were replaced with a more complex structure. So he had the kind of the solid billiard ball kind of concept. Thomson's electron discovery with the central was central with putting the probabilistic orbitals instead of his plum pudding structure, instead of that having those electrons embedded in that same more solid structure. Rutherford's nuclear structure started to be retained here with that small dense nucleus with those electrons orbiting around the outside. Chadwick's neutron completes the nuclear picture, fully integrating into this model and also accounting for the full mass of the atom. Millikan's electron charge was fundamental for these calculations, and Bohr's orbitals were the precursor to the quantum mechanical model. While we did replace those orbitals, there's still a great way to initially understand atoms as we start to progress to this modern model. In this modern atomic theory versus the quantum mechanical model, the quantum mechanical model is the modern atomic theory with refinements like corrections for the fields and really refining exactly how those orbitals and those shapes look. It does fully explain the atomic structure, the spectra, the bonding, isotopes with applications across science and technology as we look at refining and finding new materials, understanding how new materials might work. So this has kind of been a great way and an advancement. And who knows, we could refine it further even from here, but it's nice to see that progression of all those scientists' contributions to develop what we determine the modern atomic theory.